going to cover some calculations involving heat capacity and heat transfer in a system using heat, mass, temperature change, and specific heat. So let's look at our first example. This example gives you the specific heat capacity for a metal, and then we want to know how much energy is required to change the temperature of this metal by a certain amount. So we want to go from 273 to 298. Now, one thing to remember when you're using this calculation is that sometimes your delta T is positive and sometimes your delta T is negative. It depends on if you're an endothermic or exothermic reaction. So here are our values given in the problem that we're looking for heat. Here's our mass. Our specific heat of silver is given in the problem. And our delta T is always going to be your final temperature minus your initial temperature. So be sure to type those in correctly because you can get the wrong answer if you do it backwards. Now, the heat capacity is per degrees Celsius, but I want to point out that if you're talking about a change in temperature, the change in temperature for Celsius is going to be equivalent to the change in temperature of Kelvin. Because if you were to convert these Kelvin temperatures into Celsius, you're going to get the same temperature change. 25 Kelvin and 25 Celsius end up being the same thing. So when you type these formulas or these values in, you're going to get 150 for your mass. Your heat capacity is 0.24, and your delta T is 25. And you've solved those, or put those in your calculator. You get a heat of about 900 joules. Now, 900 joules is the same as 9 times 10 squared joules. So either one of those is fine. We're going to ignore the molar heat capacity for right now because that's not as important for the test. So let's look at the next calculation, number 8. Again, you're going to use the same formula. Heat is equal to the mass times the specific heat times the change in temperature. This time, however, they want to know the specific heat capacity, and they gave you the energy. So when you look at your variables, Q is given, M is given, they want C, and then they give you the change in temperature. Again, remember that the delta T goes from final minus initial. So we found that information. So now we're going to rearrange this formula for C. So the way to do that is to divide both sides by mass and delta T because that's what's being multiplied. So you're going to divide this side also by mass and delta T. And when you do that, your mass cancels and your delta T cancels, and you've isolated your C. You need to be able to rearrange formulas in chemistry effectively in order to get the right answer. So let's plug this information in. Q is equal to 585 joules. Mass is 125.6 grams. And our delta T is 33.5 degrees C. The nice thing about keeping your units in here is that when you get your answer, you will have the correct units for your answer. When you type that in, be sure to type it in yourself in your calculator. A lot of students will take this number and divide it by this number and then multiply it, and you're getting a wrong answer. So type it in yourself and make sure you're getting the right answer. Okay, now let's look at the next type of equation. This is a classic calorimetry problem. Number 9, 10, and 11, I think, are all calorimetry type problems. And basically in a calorimeter, remember what we're trying to do is avoid any heat transfer from the surroundings, which is the universe, into the system. So in this particular problem, we took a piece of copper, and that's going to be represented by this tiny little twirly part right here. We heat it up to a certain hot temperature, and then we're going to stick it into this coffee cup or this calorimeter that has water in it, and the water is cool. So then you will wait for equilibrium. Equilibrium simply means that you wait a long enough time so that both the copper and the water end up as the same final temperature. So this 21.8 is going to be our final temperature for both the metal and the water. That's what equilibrium stands for. Now, in a calorimetry problem, you want to assume that all the heat that is lost by the metal is also gained by the water. So that's what's going to help you solve this problem. So the Q, or heat lost by the copper metal, is going to be equal to the Q, or the heat gained by the water, because you simply put the hot metal inside the cold water and then you just waited for a period of time for both of them to reach equilibrium. Now, because copper is losing heat, it's an exothermic reaction, and so that's negative. And water is gaining heat, it's an endothermic reaction, so that's a positive. So when you start typing in all your information into this problem, be sure to remember that one side has to be negative and the other is positive, because one is losing heat and one is gaining heat. That's what equilibrium stands for. Now, there are 3 specific heats for water. You want to be careful about that, because is this liquid water, is this steam, or is this ice? Well, clearly this is liquid water, and so we're going to use the heat capacity for that. So when we type in or plug in our information here, we're going to use the mass of water, or I'm sorry, the mass of copper. All these subscript C means copper, and this means water. So this is the heat of the copper. So the copper is 46.2 grams, and the heat capacity of copper is what we're looking for. And then the final temperature is 21.8, because both of them reach the same final temperature. And then we're going to plug in our information on this side, 75 grams of water. And we're going to use 4.18 because that's for liquid water. And then our final temperature of the water is the same, but our initial temperature was different. All right, so then you're going to multiply this number times this number, and you'll end up getting 3400.32 C is equal to 689.7 on this side. So you divide both sides by 3400. All right, and then be sure to type this in your calculator so you get the same thing. And you get that the heat capacity is equal to 0.203. Don't forget your units. Your units are joules per gram degrees Celsius or Kelvin. Either one is fine. Let's do another one. All right. Problem number 10 is also a calorimetry problem. Okay. And you want to assume that the heat lost by the nickel, which is a metal. This metal, again, is heated up. It's dropped into some water that was cool, and then you're going to assume that all the heat lost by the nickel is absorbed by the water, and we want to know the final temperature. Again, you're going to use the same type of formula, but in this case, it's a little more tricky because you're trying to find the final temperature. Now, all I've done over here is simply take the information that was provided in the problem and put it beside each of the variables that are represented in the equation. So again, heat, over here, mCp delta T or mc delta T, and heat gained by the water, mc delta T, they're going to be equal to each other. So I'm just going to plug this information in. So it's going to be negative 15 times the heat capacity of the metal times final minus initial, which is 100, is going to be equal to the mass of the water times the heat capacity of liquid water times final minus initial of water, which is 23. Okay, now if you multiply all this stuff out on this side, you get negative 6.66 TF minus 666. Actually, it's a plus because this was negative right over here. 229.9 TF minus 287.7. Okay, now I want to solve for T final. So I'm going to go ahead and put all of my T on the same side. So I'm going to add 6.66 TF and 6.66 TF to both sides. So this goes away. And then I'm going to add 5,287 to both sides. Okay, and this goes away. So then I'll come up with 5953.7 is equal to 236.56 TF. And when I divide both sides by 236.56, I get the final temperature is equal to 25.2 degrees C. All right, and that's your answer. All right, let's look at one more before we run off this video. Number 11, Haley is running bath water and realized it was too hot. She's got 20 liters of water in the tub at 95 degrees C, so this is the hot water. Then she adds about 15.8 liters of cool water, and again, we want to know the final temperature. So it's similar to what we just did, however, it's not really a realistic scenario since she's doing it in a bathtub, which is not a correct calorimeter that has insulation that's going to keep heat from being transferred to or from the surroundings. But we're going to assume that it is. So the Q lost by the hot water, the heat lost by the hot water is going to be equal to the heat gained by the cold water. Again, one is endothermic and one's exothermic, so we need to have a plus and minus sign. We're going to use the same formula that we did before. Over here, what I've done is convert my volume, because it gave you volume and not mass, to mass by using the density of water. The density of water is 1 gram per milliliter. And then I just simply plugged in the rest of the information that's there. Now, if you'll notice, the heat capacity of liquid water and the heat capacity of liquid water, whether it's cold or hot, tends to be the same. So what we've done here is we've canceled those out because they're the same. There's no reason to have that information in there. Okay, so what we're going to do is go ahead and write this out. So negative 20,000 grams times TF minus 95 is going to be equal to 15,800 grams times TF minus 75. All right, and when you multiply that out, $15,800 TF minus 118.000. Okay, now we need to solve for TF, so I'm going to go ahead and add 20,000 TF to both sides. Okay, and that'll get rid of on this side, and then I want to go ahead and move this to the other side, so okay, and this goes away, so you end up with some pretty big numbers. Okay, and you divide both sides by the coefficient, and you get your final temperature of 86.2 degrees C. And that's pretty much how you do all your calorimetry problems. Good luck.